at the bones of ancient creatures, often focusing on the size of their teeth or the power of their limbs. But there's another story, one equally dramatic, equally important, and far more enduring. It's the story of armor. Not the armor forged by human hands in castles and battlefields, but armor grown from living tissue, sculpted by natural selection, and refined through countless generations until it became a masterpiece of biological engineering. Some of these armored creatures dominated their worlds for hundreds of millions of years, far longer than any other dominant life form we know of. And though many have faded into extinction, their legacy persists in the living armored animals that walk, swim, and crawl across our world today. This documentary will take us from the moment the first predators emerged in Earth's oceans, spurring an evolutionary arms race that would revolutionize life itself. We'll examine how simple shells became sophisticated exoskeletons. We'll watch as fish developed heavy plating, as reptiles grew thick hides and bony protrusions, and as mammals created some of the most unusual defensive structures ever to evolve. We'll see how environmental pressures shaped these remarkable adaptations, and why, despite their apparent invulnerability, so many of these armored giants ultimately succumbed to extinction. And we'll discover why even today, after all these millions of years, creatures continue to invest in armor as a survival strategy. Please let us know in the comments where you are watching this history video and what time you are watching it, and be sure to subscribe to the channel for future videos. Now, let's begin our exploration of the Age of Armor. Part 1, the Genesis of Defense. To understand why armor became so important in the history of life, we must first understand the world before it. For the first 3 billion years of life's existence on Earth, creatures were soft-bodied. They were simple. Bacteria, algae, sponges, and other early organisms floated and crawled through the oceans without any rigid structures. There were no teeth, no claws, no hard parts at all. And in this world, there was little need for defense because there were few predators capable of hunting anything larger than themselves. But something profound changed around 540 million years ago, during a period we call the Cambrian Explosion. This was an era of revolutionary biological innovation, where new body plans emerged at an astonishing rate. In a relatively brief window of geological time, perhaps just a few million years, most of the major animal groups that exist today either originated or developed distinguishable characteristics. And crucially, among these new innovations were predators. The emergence of predators fundamentally altered the evolutionary landscape. For the first time, being larger or more complex offered no guarantee of safety. Creatures that had survived for millions of years suddenly found themselves under attack from smaller, faster organisms equipped with primitive hunting strategies. This created what evolutionary biologists call an arms race, a reciprocal evolutionary process where predators develop better weapons and prey develop better defenses, each spurring the other to greater refinement. One of the most effective defenses that emerged during this arms race was armor. And the first creatures to develop it were among the most successful animals ever to inhabit Earth. The trilobites, architects of armor. When we speak of the first great armored animals, we cannot avoid discussing the trilobites. These creatures, which first appeared in the fossil record around 520 million years ago, represent perhaps the earliest sophisticated example of exoskeletal armor in the animal kingdom. They would go on to dominate marine environments for nearly 300 million years, making them one of the longest-lasting dominant groups of animals in Earth's history. The name trilobite comes from the 3 lobes that run along the length of their bodies, a central axial lobe and 2 pleural lobes on either side. But this segmented structure was far more than just a distinctive feature. It was a solution to a fundamental problem: how to combine protection with mobility. A solid shell, while protective, is restrictive. It prevents movement. The trilobites solved this problem through their segmented exoskeleton, which allowed them to curl into tight balls when threatened, presenting an armored sphere to predators while maintaining flexibility for movement and feeding when uncurled. The segments of their exoskeletons were made of chitin, a polymer substance that is strong, lightweight, and can be calcified to create even greater rigidity. Over time, trilobite species developed increasingly elaborate exoskeletons, with some developing spines, ridges, and other structures that made them even more difficult to attack. The exoskeleton itself required regular maintenance and replacement. As trilobites grew, they would periodically shed their old exoskeleton and grow a new one, a process called molting. During these vulnerable moments, they were exposed to predators. However, many trilobites developed behavioral strategies risk. Some species would molt in protected environments, such as shallow crevices or within sediment, reducing their exposure. Others seem to have molted rapidly, perhaps driven by predation pressure to spend as little time as possible without their protective armor. The success of the trilobite design was staggering. Over their long history, trilobites diversified into thousands of species, adapted to nearly every marine environment on Earth. Some were tiny, just a few millimeters in length. Others, like the genus Isotlus, could grow to nearly 3 feet long. Some were blind, living in deep, dark waters where eyes were unnecessary. Others had compound eyes so sophisticated that they rival the vision of modern insects. This diversity speaks to the fundamental soundness of the trilobite body plan. But the trilobite story tells us something crucial about armor as a survival strategy. For all their sophistication, for all their success, trilobites were ultimately specialized for a particular set of environmental conditions. They thrived in warm, shallow seas where food was abundant and predators were relatively simple. When environmental conditions changed, when the oceans became more complex, when new and more sophisticated predators emerged, the trilobites' advantage diminished. They would persist until the end of the Permian period, over 270 million years after their first appearance, but their dominance would not last forever. The Ordovician early armor diversification, the period following the Cambrian, known as the incredible radiation. Not all of these were exoskeletons like those of trilobites. Evolution was experimenting with many different defensive solutions, and armor, it seemed, was one of the most promising. During the Ordovician, we see the emergence of the first armored fish. These creatures, which we call ostracoderms, or more recently, jawless fish or agnathins, developed bony plates that covered their heads and bodies. Unlike the chitin of trilobite exoskeletons, these early fish had structures made of bone, a calcium phosphate compound that is even stronger and more like chitin. The earliest known ostracoderm record around the beginning of the Ordovician period, 485 million years ago, but these were not primitive creatures. Even the earliest known forms show signs of sophisticated anatomical organization. They had eyes, mouths, and intricate systems of organs that were protected from armor. The fact that they appeared already well formed in the fossil record suggests they had a longer evolutionary history not yet captured in the rocks we have found. These early armored fish were small, typically only. They inhabited shallow marine environments and seemed to have been filter feeders or consuming organic particles from the water or the sea floor. Their armor provided protection from the increasing variety of predators that hunted in these seas. Predators including early cephalopods, large arthropods, and some of the larger trilobites that had also evolved predatory lifestyles. The development of bony armor in fish represented a significant innovation in the history of life. Bone is metabolically expensive to produce and maintain. It requires more energy than chitin, but it offers several advantages. It is stronger, more rigid, and can form complex shapes more easily. Bone can also be remodeled more readily than chitin, allowing growth while maintaining protection. This flexibility would prove crucial as fish continue to evolve and diversify. Throughout the Ordovician and into the Silurian period which followed, ostratified greatly, has developed different body configurations. Some remain small and flatly adapted lore, streamlined, swimmers, elaborate along the sides structures called lateral could detect for hunting in murky sea. The armor of the not uniform species have strategies. Some had smooth, streamlined plates that reduced drag in the water. Others developed keels and ridges that provided rigidity. Some had small openings that allowed water to flow through specific areas, perhaps for improved hydrodynamic efficiency. The variety of solutions suggests that natural selection was actively fine-tuning these defensive structures, exploring the space of possible designs to find optimal configurations for different ecological niches and hunting strategies. The placoderm's armor reaches its pinnacle. If the ostracoderms represented the first great age of armored fish, the placoderms represented the culmination of that design philosophy. Placoderms first appeared in the Silurian period and would dominate marine ecosystems through the Devonian period, an era sometimes called the Age of Fish, because of the incredible diversity and abundance of fish that populated the oceans during this time. The placoderms were unlike anything that had existed before. While they retained some similarity to their ostracoderm ancestors, placoderms represented a significant evolutionary innovation. They developed jaws, a feature that made them far more effective predators than their jawless ancestors. But more importantly for our study, they developed some of the most spectacular armor ever to exist in the history of life. The term placoderm comes from the Greek words meaning plate and skin, referring to the large bony plates that covered their bodies. These were not small, overlapping scales like those of modern fish. These were massive, interlocking plates that covered the head, body, and often extended into elaborate defensive structures. Some placoderms developed spines extending from their armor. Others had plate configurations that created an almost impregnable fortress of bone. Consider a creature like Dunkleosteus, which lived during the late Devonian period, roughly 370 million years ago. This was a giant among placoderms, reaching lengths of up to 33 feet, larger than most modern sharks. Its entire head and body were encased in heavy armor, but Dunkleosteus was not merely a passive, heavily armored creature. Instead, it was an active, sophisticated predator. Its armor contained openings for eyes, for a complex sensory system, and most importantly, for a mouth full of shearing plates instead of teeth, structures called keratinous plates that could bite with devastating force. Dunkleosteus represents a crucial principle in the evolution of armor. Protection and performance were not mutually exclusive. Indeed, some of the most successful armored creatures were not slow, lumbering tanks, but rather dynamic hunters and swimmers that used their armor to enable, rather than inhibit, their predatory lifestyle. The heavy plates of Dunkleosteus provided protection, while its sleek body shape allowed it to accelerate rapidly and maneuver with surprising agility for a creature of such size. Other placoderms developed different armor configurations tailored to different lifestyles. Some small placoderms remained relatively lightly armored, seemingly adapted for feeding on smaller organisms in shallow waters. Others developed elaborate spines and projections, creating structures so complex that they might have served multiple purposes: protection, species recognition, or even dominance display during social interactions. The Devonian seas saw the evolution of increasingly elaborate armor among placoderms. This suggests that predation pressure was constantly increasing, selecting for more effective defensive designs. Each innovation in attack was met with an innovation in defense. Predators evolved more powerful jaws and more sophisticated hunting strategies. Prey species evolved heavier armor, more complex plate configurations, and defensive structures like spines. This arms race led to some remarkable outcomes. Some placoderms evolved armor so heavy that they may have struggled with mobility. The cost of protection was reduced speed and agility. Others evolved lighter armor but in more sophisticated configurations, achieving protection through clever engineering rather than brute mass. The diversity of placoderm designs suggests that there were multiple ways to balance protection and performance, and natural selection was exploring all of them simultaneously across many different species and lineages. The cost of armor, metabolic and structural constraints. As we examine the incredible diversity of armored creatures, we must address an important question. What is the cost of armor? Why don't all creatures develop protective structures? The answer lies in understanding that armor is expensive, both in terms of energy and in terms of evolutionary trade-offs. Producing and maintaining armor requires metabolic energy. Bone, in particular, is metabolically costly. It must be synthesized using calcium and phosphorus, minerals that must be obtained from the environment. Once formed, bone tissue is not inert. It is living tissue containing cells that require oxygen and nutrients. Maintaining an exoskeleton or bony armor requires a substantial portion of an organism's energy budget. This means that a heavily armored creature must consume more food than an unarmored creature of similar size just to maintain its protective structures and the rest of its body. This metabolic cost creates a constraint. In environments where food is scarce, armor becomes a liability rather than an asset. A creature that invests heavily in armor in a food-poor environment may starve before it is ever threatened by predation. This is one reason we see such variation in armor investment across different species and environments. Species in resource-rich environments can afford to be heavily armored. Species in resource-poor environments must remain lighter and more mobile, sacrificing protection for the ability to hunt or forage more efficiently. There is another cost to armor: weight. An armored creature is necessarily heavier than an unarmored creature of the same body size. This affects how it moves through its environment. A heavily armored creature cannot climb, cannot move as quickly, and may even struggle to remain buoyant in water. For many creatures, this trade-off is worthwhile. The protection provides more benefit than the loss of mobility costs. But for creatures that rely on speed to capture prey or escape predators, armor may be too costly. Furthermore, armor creates constraints on body shape and movement. An exoskeleton is rigid and must be shed and regrown as the creature grows. During molting, the creature is vulnerable. An internal skeleton, such as the bones that support most modern vertebrates, can grow continuously without the vulnerability of periodic molting. This is one reason that many modern creatures do not develop armor. They rely instead on internal skeletons that provide support without the necessity of vulnerable molting periods. Armor also affects feeding. A heavily armored mouth may be strong, but it can be slow to open and close. A creature with a delicate, unarmored face can eat a wider variety of food and process it more efficiently. This is why we often see that heavily armored predators like Dunkleosteus are specialists. They can eat certain types of prey very efficiently, but they cannot consume a wide variety of different foods. These constraints mean that armor is not a universally superior strategy. Instead, it represents a solution optimized for particular ecological situations. Armor works well for creatures that are, first, large enough to carry the extra weight without significant loss of agility. A small creature's weight is more dramatically affected by the addition of protective structures than a large creature's weight. Second, living in environments where they can afford the metabolic cost of maintaining the armor. In environments with abundant food, this cost is easily borne. In sparse environments, it may be prohibitive. Not dependent on extreme speed or escaping predators. Armor works best for creatures that either to deter predators that cannot outrun them. Fourth, living in environments where the predation pressure justifies the investment in protection. If predators are rare or weak, armor is an unnecessary expense. If predators are abundant and dangerous, armor becomes essential. These constraints shape the distribution of armor throughout Earth's history. We see it most commonly in large creatures living in resource-rich environments with significant predation pressure. We see it less commonly in small creatures, in resource-poor environments, or in environments with low predation pressure. The Devonian diversity, an ecosystem in armor. The Devonian period, spanning roughly from 420 million to roughly 360 million years ago, represents a pinnacle of armored life diversity. During this time, the oceans were home to an astonishing array of armored fish. Placoderms dominated, but they were not alone. Sharks and early bony fish also evolved, and some of these also developed armor, though in different forms than the massive plates of the placoderms. The early sharks that evolved during the Devonian were not the sleek, flexible hunters we know today. Many were more heavily built, some with large spines protruding from their bodies. These spines seem to have served a defensive purpose, making the shark a more formidable opponent for predators. Some early sharks also developed elaborate body shapes with fins and crests that may have served both hydrodynamic and defensive functions. The early bony fish of the Devonian also diversified greatly. These creatures, which would eventually give rise to all modern fish with skeletons of bone rather than cartilage, developed many different body forms. Some were lightly armored with only modest bony reinforcement of their scales. Others were heavily armored with thick plates and strong bones. These early bony fish exploited ecological niches that the placoderms did not fully occupy, hunting smaller prey or living in different water depths. The Devonian seas were a complex ecosystem with multiple levels of predation. At the top were the largest placoderms, creatures like Dunkleosteus, which hunted large prey. Below them were smaller placoderms, sharks, and large bony fish, which hunted medium-sized prey. At the bottom of the food web were vast numbers of small fish, arthropods, and other organisms that fed on organic particles and each other. In this complex ecosystem, armor served different purposes for different creatures. For large predators like Dunkleosteus, armor protected them from other large predators and from powerful prey that might struggle when caught. For smaller fish, armor protected them from mid-sized predators. And for the smallest creatures, even modest armor provided significant protection against creatures only slightly larger than themselves. The arms race during the Devonian was perhaps more intense than anything that had occurred before. Not only were there more species in competition with each other, but the predators were becoming more sophisticated. As predators evolved more powerful jaws and better hunting strategies, prey species responded by evolving more elaborate armor and better defenses. Some of the most extreme examples come from creatures called the antiarchs, a group of placoderms that developed in a radically different direction from their armor-plating relatives. Antiarchs developed large, flipper-like appendages that seem to have served both locomotor and feeding functions. Unlike most other placoderms, which were primarily marine, some antiarchs invaded freshwater environments. Their armor allowed them to survive in these challenging habitats, which were often turbulent, with strong currents and abrasive sediments. The armor protected them from the rough conditions as much as from predators. Armor in the air, the first flying creatures. While our focus has been primarily on aquatic creatures, we must not neglect to mention that armor also appeared in some of Earth's first flying creatures. During the Carboniferous period, roughly 300 to 320 million years ago, insects were among the most successful land animals. Some insects evolved protective structures, thickened exoskeletons, tough wings, and other reinforcements that served defensive purposes. But more significantly, the first vertebrates to achieve true flight were the pterosaurs, which appeared during the Triassic period, around 250 million years ago. While pterosaurs were not heavily armored in the way that placoderms were, many species did have thickened skin, and some had crests and projections that may have served protective functions. The very act of flying required modifications to their skeletons and musculature that, while not primarily defensive, did provide some measure of protection. However, the primary point is that armor as a dominant strategy was not exclusively aquatic. The success of armor in the oceans seems to have inspired similar solutions in other environments, adapted to the specific challenges of those habitats. The decline of the placoderms and the rise of modern fish, the Devonian period, for all its dominance of placoderms, was not the end of the story of these armored fish. Indeed, the Devonian witnessed not just the height of placoderm success, but the beginning of their decline. By the end of the Devonian period, roughly 360 million years ago, the placoderms were beginning to disappear from the fossil record, and by the beginning of the Carboniferous period, they were entirely extinct. The extinction of the placoderms was not sudden. Instead, it seems to have been a gradual process, with placoderm diversity declining over several million years. The exact causes remain debated among paleontologists, but several factors seem to have contributed. First, sharks were diversifying and becoming more sophisticated. Many modern shark lineages arose during the Devonian, and these creatures possessed advantages over placoderms. Sharks had flexible, cartilaginous skeletons that allowed greater mobility than the rigid armor of placoderms. They had more sophisticated sensory systems, particularly the ability to detect electrical fields generated by muscle contractions in other creatures. And they had simpler, more efficient feeding mechanisms that could be positioned, allowing them to adjust their feeding strategy to match available prey. Second, early bony fish were also diversifying and becoming more efficient. These creatures could achieve many of the ecological roles that placoderms filled, but with greater flexibility and efficiency. Bony fish could grow continuously without molting, they could achieve more sophisticated body shapes, and they could evolve specialized feeding mechanisms for specific prey types. Third, environmental changes during the late Devonian seem to have stressed many marine ecosystems. Ocean oxygen levels declined in some regions, creating hypoxic zones where only creatures adapted to low oxygen conditions could survive. Sea levels also fluctuated, altering the habitats available for different creatures. In these changing conditions, the specialized placoderms, which were adapted for particular ecological roles, may have found themselves unable to adjust. Finally, the very armor that had protected placoderms from predators may have become a liability in changing conditions. The massive plates that provided such effective protection were also metabolically expensive and had limited flexibility. In environments where predation pressure decreased or where environmental conditions changed rapidly, the investment in this heavy armor became less worthwhile, and more flexible creatures with lighter protection gained an advantage. The extinction of the placoderms illustrates an important principle about armor and survival. Armor is not an absolute defense. Instead, it is a strategy adapted to particular conditions. When those conditions change, armor may become less effective or even maladaptive. The transition to terrestrial armor, the first land animals, around 360 million years ago, at roughly the same time that placoderms were beginning to decline, something equally revolutionary was happening on land. The first tetrapods, four-legged vertebrates, were beginning to emerge from the water and venture onto dry land. These creatures faced entirely new challenges and opportunities, and armor would play a crucial role in their success. The earliest tetrapods, creatures like Acanthostega and Ichthyostega, were not highly armored in the way that placoderms were. Instead, they had relatively simple body structures inherited from their fish ancestors. However, they did have scales and thickened skin that provided some protection against abrasion and drying out. As tetrapods diversified and became increasingly committed to life on land, many lineages evolved more sophisticated armor and protective structures. One of the most notable early tetrapod groups was the Temnospondyli, a diverse lineage of semi-aquatic creatures that dominated freshwater and some marine environments during the Carboniferous and Permian periods. Some temnospondyls evolved thickened skulls and body armor that provided protection against both predators and the abrasive environments they inhabited. These creatures ranged from small, salamander-like animals to large predators that hunted other tetrapods. Another important group was the Sauropsida, the lineage that would eventually give rise to modern reptiles. Among early sauropsids, we see the evolution of various protective structures. Some developed thickened scales, others developed bony dermal plates that lay beneath their skin, and some developed elaborate spikes and crests that served both defensive and display functions. The Permian period, which lasted from roughly 300 million to 251 million years ago, saw an extraordinary diversity of armored tetrapods. One of the most striking examples was the Synapsida, a group of creatures that are sometimes called mammal-like reptiles because they shared characteristics with both modern reptiles and modern mammals. Among synapsids, we find some remarkably armored creatures. Dimetrodon, a synapsid from the early Permian, is perhaps one of the most famous early tetrapods, primarily due to the enormous sail on its back, a structure formed by elongated spines extending from the vertebrae. This sail was likely used for thermoregulation, allowing the creature to absorb heat from the sun. However, the spines themselves constituted a form of armor, making the creature a less tempting target for predators. Any predator attempting to bite a Dimetrodon would have to contend with these sharp spines. Other synapsids developed different protective structures. Some became heavily built, with massive bones and powerful jaws. Others developed thick skulls that may have been used in intraspecific combat, fighting between members of the same species. The diversity of Synapsida suggests that armor in all its forms was becoming increasingly important as a survival strategy on land. The Permian period, the zenith of armor on land. The Permian period represents perhaps the most diverse array of armored land animals ever to exist. During this time, tetrapods had diversified into hundreds of species, occupying nearly every available ecological niche, and many of these species had evolved sophisticated defensive and protective structures. The Periasaurs were particularly heavily armored creatures of the Permian. These were large, barrel-bodied reptiles that reached lengths of up to 10 feet. Their entire bodies were covered with bony osteoderms, bony plates embedded in the skin that provided substantial protection. Their heads were also heavily reinforced with bony plates, and some species developed elaborate spikes and protrusions along their backs and shoulders. These were slow-moving, herbivorous creatures that relied on their armor rather than speed to avoid predation. The Dicynodonts were another major group of Permian synapsids. Unlike most other synapsids, Dicynodonts were herbivorous, feeding on the vegetation that was becoming increasingly abundant during the Permian. Many Dicynodonts were relatively lightly armored compared to Periasaurs, but they were not completely unprotected. Some had thickened bones, some had specialized teeth that could be used defensively, and some had developed unusual body shapes that may have served protective functions. Among carnivorous synapsids, we see the saber-toothed sphenacodonts, which hunted other tetrapods. These creatures, the ancestors of mammals, were not heavily armored. Instead, they relied on speed, agility, and powerful jaws for hunting. However, some species did develop modest protective structures, suggesting that even active predators benefited from some degree of protection against other predators. The Eosauropsids and other sauropsids of the Permian also showed considerable armor diversity. Some early members of the Archosauromorpha, the lineage that would eventually give rise to dinosaurs and crocodilians, developed protective structures. Proterosuchians, early archosaurs, had moderately thickened skulls and some degree of body armor, though not as elaborate as that of Periasaurs or other specialized defensive forms. One of the most striking Permian creatures was Proterosaurus, an early archosaur that reached lengths of up to 6 feet. This creature had an elegant body shape, suggesting it was an active hunter, but it also had a moderately reinforced skeleton, indicating that protection was important even for predatory forms. The Permian also saw the evolution of marine reptiles, some of which developed armor. The mesosaurs, early Permian reptiles that returned to the sea, had somewhat thickened skulls and reinforced bodies, though they were not heavily armored compared to contemporary terrestrial forms. Later, during the Permian, other marine reptiles evolved, some of which developed more substantial protective structures. The significance of the Permian armor diversity, the extraordinary diversity of armored creatures during the Permian, tells us something important about the state of tetrapod evolution at this time. predation pressure was apparently intense. The variety of armor types, from the plates of periasaurs to the modified body shapes of dicynodonts to the thickened skulls of various synapsids, suggests that evolution was exploring many different solutions to the problem of protection. Furthermore, the success of these armored creatures is evident from their abundance in the fossil record. Periasaurs and dicynodonts are among the most common fossils found in Permian rock formations. They were clearly successful strategies for surviving in Permian ecosystems. Yet the Permian also illustrates another principle: armor is not a universal strategy. Many Permian creatures remained relatively unarmored. Some of the most successful predators had minimal armor, relying instead on speed and agility. This suggests that there were multiple valid strategies for survival, and evolution was supporting a diversity of approaches. The Permian would reach an apex of tetrapod diversity and complexity. Many lineages were thriving, each adapted to particular ecological roles. Herbivores of various sizes filled different niches. Predators of various sizes hunted different prey. And many of these creatures had evolved sophisticated protective structures, armor, that allowed them to exploit ecological roles that would have been impossible without such protection. But the Permian period would not last forever, and the end of the Permian would bring changes so dramatic that they would reshape the entire course of tetrapod evolution and the history of armor on land. The end of the Permian and the Permian-Triassic extinction, roughly 251 million years ago, at the boundary between the Permian and Triassic periods, Earth experienced the most severe mass extinction event in its history. This event, known as the Permian-Triassic extinction, or the Great Dying, eliminated roughly 96% of all marine species and 70% of all terrestrial vertebrate species. The causes of this extinction are not fully understood, but evidence suggests that a combination of factors was responsible. Massive volcanic eruptions in Siberia, known as the Siberian traps, released enormous quantities of carbon dioxide and other gases into the atmosphere. This triggered rapid climate change and ocean acidification. The oceans became severely oxygen depleted, creating conditions that only specialized creatures could survive. On land, the climate became harsher, with extreme temperature swings. The atmospheric composition changed, possibly becoming toxic to some creatures. Meteorite impacts may also have occurred around this time, though evidence for this is debated. Regardless of the exact causes, the result was catastrophic. Entire ecosystems collapsed. Creatures that had been dominant for millions of years suddenly went extinct. The heavily armored creatures of the Permian were particularly hard hit. The periasaurs, with their massive bodies and slow metabolism, could not adapt quickly to the changing conditions. The dicynodonts, despite their diversity, were also severely depleted. Many synapsid lineages were entirely eliminated. By the time the Permian-Triassic extinction had run its course, the world had changed so dramatically that the survivors would need to adopt entirely new strategies for survival. The extinction of these heavily armored creatures illustrates a crucial point about armor: it is only advantageous in stable environmental conditions. When environments change rapidly, creatures that have invested heavily in specialized structures may find themselves at a disadvantage. The flexible, adaptable creatures that survived the Permian-Triassic extinction were not necessarily the most heavily armored. Instead, they were creatures that had less elaborate specializations and could more readily shift their behavior and physiology in response to changing conditions. The Triassic Recovery and New Armored FORMS, the Triassic period, which lasted from approximately 251 million to 200 million years ago, saw the recovery of life from the Permian-Triassic extinction. Many old lineages had been destroyed, but survivors diversified to fill the ecological niches left vacant. And among the creatures that evolved during the Triassic were many that developed armor, though different forms than those of the Permian. One of the most important new groups to emerge were the dinosaurs. The earliest dinosaurs appeared during the early Triassic, around 245 million years ago. These creatures inherited from their synapsid ancestors a relatively unspecialized body form that would prove extraordinarily flexible. Over the course of the Triassic, dinosaurs diversified, eventually becoming the dominant terrestrial vertebrates. Many early dinosaurs were lightly armored or unarmored. The early theropods, bipedal predators that would eventually give rise to birds, were generally not heavily armored. The early sauropods, which were among the largest creatures ever to exist, also tended to be lightly armored, though their sheer size provided protection against most predators. However, some early dinosaurs did develop armor. The Ornithischian dinosaurs, a diverse group that included herbivorous forms, evolved various protective structures. Some developed thickened bones, some developed spikes or plates along their backs, some developed elaborate head structures that may have served defensive functions. Among other Triassic creatures, armor was more prominent. Placodonts, marine reptiles that were specialized shell eaters, developed strong jaws and thickened skulls that allowed them to crush shellfish. The nothosaurs and plesiosaurs, other marine reptiles, had streamlined bodies but some degree of skeletal reinforcement that provided protection. The crurotarsans, the group that would eventually give rise to modern crocodilians, also evolved during the Triassic. Some early crocodilians developed thickened osteoderms, bony plates in the skin that provided. These structures would become increasingly elaborate in later crocodilians. The Jurassic period, armor diversifies on a grand scale. The Jurassic period, spanning from roughly 200 million to 145 million years ago, is perhaps most famous for the existence of enormous dinosaurs, the sauropods and large theropods that captured popular imagination. But the Jurassic was also a period of extraordinary diversification in armored forms. During the Jurassic, dinosaurs continued to evolve in myriad directions. The theropods became larger and more sophisticated predators. The sauropods became even more enormous, reaching sizes that stagger the modern imagination. But the herbivorous ornithischians underwent a particularly important diversification. The stegosaurs were one of the first ornithischian groups to develop elaborate armor. These creatures, which reached lengths of up to 30 feet, had distinctive rows of large bony plates extending along their backs from the neck to the tail. Additionally, they had large spikes protruding from their tails. These structures were formidable defensive weapons. A predator attacking a stegosaur would have to contend with rows of sharp plates, and if it got too close to the tail, it risked severe injury or death from the tail spikes. The exact function of the stegosaur plates has been debated. Some paleontologists argue they were primarily defensive. Others suggest they served thermoregulatory functions, allowing the stegosaur to adjust its body temperature by adjusting the blood flow to the plates. Most likely, they served multiple functions, providing both protection and thermoregulation. The ankylosaurs appeared during the Jurassic and would continue to diversify and become increasingly heavily armored through the subsequent Cretaceous period. The earliest ankylosaurs were relatively lightly armored compared to their later descendants. However, they already showed the basic characteristics that would define the group: heavy body armor composed of thickened osteoderms, sturdy limbs, and a generally low center of gravity. These creatures were built like tanks, slow, powerful, and nearly invulnerable to predation. The ornithopods, another major ornithischian group, were generally not heavily armored. Instead, they were smaller, more agile creatures that relied on speed and intelligence to evade predators. Some ornithopods did develop modest protective structures, but most were relatively lightly armored compared to stegosaurs or ankylosaurs. In the oceans, the Jurassic was home to many marine reptiles. The plesiosaurs, with their flippers and streamlined bodies, were active swimmers that preyed on fish and other marine creatures. While some plesiosaurs had reinforced skeletons, they were not heavily armored. The ichthyosaurs, dolphin-like marine reptiles, were similarly built for speed and agility rather than defense through armor. However, some marine creatures did develop substantial armor. The mosasaurs, which appeared later during the Cretaceous but had earlier relatives, were powerful predators with thickened skulls and robust skeletons. And the turtles, which evolved during the Triassic and became increasingly prominent during the Jurassic, had developed their characteristic shells, among the most successful armor designs in the history of life. The turtle shell, an evolutionary masterpiece. The evolution of the turtle shell deserves special attention because it represents one of the most elegant solutions to the problem of protection that evolution has ever produced. Turtles appeared in the fossil record during the Triassic period, around 220 million years ago. The earliest turtles, creatures like Progonocles, already had shells, suggesting that the shell evolved before the earliest turtles left fossil evidence. The turtle shell is constructed differently from the plates and spines of other armored creatures. Instead of being composed of separate structures that protect the body, the shell is integrated with the skeleton. The carapace, the upper part of the shell, is formed from the fusion of the vertebrae and ribs, covered by horny scutes, tough, plate-like structures made of keratin. The plastron, the lower part of the shell, is formed from bones that develop in the skin. This construction is remarkable because it means that the turtle's skeleton itself is the shell. The turtle cannot leave its shell behind as other creatures can shed their exoskeletons. Instead, the turtle has evolved to live inside its own skeleton. The advantages of this design are numerous. The shell provides near-total protection from predators. A predator attempting to bite a turtle must contend with a hard, inflexible surface that offers no purchase for teeth or claws. Turtles that live on land can retreat into their shells and close them off with a hinged plastron, creating a nearly impenetrable fortress. Aquatic turtles, unable to close their shells, rely on the rigidity of their shells and their aquatic lifestyle to escape predators. The shell also provides protection from environmental hazards. It insulates the turtle from temperature extremes. It protects against abrasion and rough surfaces. It allows turtles to survive in harsh environments where other creatures would be injured or killed. However, the shell also imposes constraints. Turtles must bear the weight of their shells throughout their lives, which limits their speed and agility. Turtles have a slower metabolism than many other reptiles, partly because the energy cost of carrying their heavy shells is substantial. Turtles grow relatively slowly and reach reproductive maturity relatively late in life. All of these traits are correlates of their heavy armor investment. Nonetheless, the turtle shell has proven to be an extraordinarily successful design. Turtles have persisted largely wrapping yourself in nature's most sophisticated engineering. Created a crater nearly 100 miles across and released energy equivalent to billions of nuclear weapons. The impact and subsequent volcanism released vast quantities of dust and gases into the atmosphere, blocking out the sun for months or years. Temperatures plummeted, photosynthesis ceased. The food chains that supported all life began to collapse. This extinction event was particularly devastating for large creatures. The largest dinosaurs went extinct. The marine reptiles, including mosasaurs and plesiosaurs, disappeared. Many marine creatures died off. On land, most creatures larger than roughly 25 pounds went extinct. The survivors tended to be small, with rapid generation times and the ability to survive on limited food for extended periods. Importantly, many armored creatures went extinct during the KPG event. The ankylosaurs, despite their armor, could not survive the collapse of plant-based food chains that resulted from the darkness following the impact. The ceratopsians similarly perished. The great armored dinosaurs that had dominated terrestrial ecosystems for tens of millions of years vanished in what, on a geological timescale, was an instant. However, some armored creatures survived. Turtles, despite being large and having heavy armor, survived the KPG extinction. The reason for their survival is not entirely clear, but several factors may have contributed. Turtles could potentially survive on limited diets. They might have eaten plants, detritus, or even animal carcasses, all of which might have been available even in the bleak post-impact world. Aquatic turtles in particular may have been buffered from the worst effects of the extinction, as aquatic ecosystems, while severely disrupted, may not have been as completely devastated as terrestrial ecosystems. Crocodilians also survived the KPG extinction. Like turtles, crocodilians developed osteoderms, bony plates in the skin, that constituted a form of armor. Crocodilians were relatively small during the KPG extinction, much smaller than they would become in later periods. Their small size, rapid reproduction, and ability to survive on minimal food for extended periods made them good candidates for survival through the extinction event. Other survivors included small lizards, some snakes, and various invertebrates. But among large tetrapods, armored forms were notably rare among the survivors. The post-extinction world and the rise of mammals, the 66 million year period between the KPG extinction and the present, represents an era of dramatic evolutionary change. In the absence of dinosaurs, mammals, which had previously been small, largely nocturnal creatures, underwent enormous diversification. Some of these mammals evolved armor, though the forms of armor were different from those that had protected dinosaurs. Among the first mammals to develop armor were the glyptodonts, large armored mammals that first appeared in the fossil record around 55 million years ago. These creatures were related to modern armadillos and belonged to the xenarthrans, a group that also includes anteaters and sloths. Glyptodonts were among the first large terrestrial herbivores to evolve after the extinction of dinosaurs, and their armor was a crucial adaptation that allowed them to grow large enough to escape predation. The armor of glyptodonts consisted of bony osteoderms fused together to form a solid carapace, a bony shell that covered most of the animal's body. In many ways, the glyptodon's armor was similar to the armor of ankylosaurs, though it evolved independently and through different mechanisms. This independent evolution of similar armor designs in distant lineages, a phenomenon called convergent evolution, indicates that such armor is a powerful solution to the problem of protection. Glyptodonts ranged in size from creatures roughly as large as modern armadillos to giants like Glyptodon clavipes, which reached lengths of nearly 13 feet and weighed up to 4 tons. These massive creatures were slow and ponderous, but their armor made them nearly invulnerable to predators. A Glyptodon could simply shell up and wait out an attack from a predator, secure in the knowledge that few creatures could penetrate its carapace. Like the ankylosaurs before them, glyptodonts had tail structures that could be used for defense. Some had club-like tail ends, others had spiked tails. These could deliver devastating blows to predators or rival glyptodonts. The success of glyptodonts suggests that large armor is a viable strategy even in the post-dinosaurian world. For roughly 45 million years, from their first appearance around 55 million years ago to their extinction roughly 10,000 years ago, glyptodonts were successful inhabitants of South American ecosystems. Their armor was as effective against the predators of their time, including large saber-toothed cats, as dinosaurian armor had been against dinosaurian predators. Summary of Part 1, the story of armor through deep time. As we conclude the first part of our exploration of the forgotten age when creatures wore armor, we can see that armor has been a persistent and successful survival strategy for more than 500 million years. From the trilobites of the Cambrian through the placoderms of the Devonian, from the heavily armored tetrapods of the Permian through the Ankylosaurs and ceratopsians of the Cretaceous, and into the glyptodonts of the Cenozoic, armor has allowed countless creatures to protect themselves and exploit ecological niches that would have been impossible without such protection. The repeated evolution of armor in different lineages and different eras suggests that it is a fundamentally sound survival strategy under particular conditions. When predation pressure is high, when environmental resources are abundant enough to afford the metabolic cost of armor, and when environmental conditions are stable enough that creatures can rely on specialized adaptations, armor becomes an attractive evolutionary solution. Yet armor is not without costs and constraints. It imposes metabolic demands, it limits mobility, it makes creatures vulnerable during molting or growth, it makes rapid adaptation to changing conditions more difficult. These constraints mean that armor is not universally advantageous. Instead, it represents a set of trade-offs, trading speed and flexibility for protection. We have seen that when environmental conditions change dramatically, as they did at the Permian-Triassic boundary and at the KPG extinction, armored creatures may be particularly vulnerable. The very specialization that makes armor effective in stable conditions makes it less effective in rapidly changing conditions. Evolution has explored many different solutions to the problem of survival, and armor is just one of those solutions. In the second part of this documentary, we will examine how armor has continued to evolve and persist into the present day, explore the living armored creatures that carry forward ancient designs, and consider what the persistence of armor tells us about the nature of evolution and the strategies that life has discovered for surviving in a competitive world. But before we move to Part 2, let us reflect on what we have learned in this first part. We have traced the evolution of armor from its origins in the Cambrian Explosion through more than 500 million years of evolutionary history. We have seen how armor has been reinvented, refined, and adapted to countless different body plans and ecological roles. And we have seen that while armor is not an absolute defense against the forces that shape evolution, extinction, environmental change, and ecological competition, it has proven to be one of the most durable and successful strategies in the history of life. Thank you for joining us on this journey through the forgotten age when creatures wore armor. In Part 2, we will continue our exploration and discover how the ancient wisdom written into the bodies of armored creatures continues to influence life in our modern world. Welcome back to the forgotten age when creatures wore armor. In the first part of this documentary, we trace the evolution of protective structures from the earliest armored creatures of the Cambrian Explosion through the extinction of the dinosaurs and the rise of armored mammals like the glyptodonts. We discovered that armor, despite its considerable costs, has been a persistent and successful survival strategy for more than 500 million years. We saw how armor evolved independently in multiple lineages, how it was refined and adapted to countless ecological roles, and how environmental changes sometimes rendered even the most sophisticated armor ineffective. Now in Part 2, we will explore what happened to armor after the fauna extinction, has continued to rely on armor as a survival strategy, of armor into the present day, the nature of evolution, adaptation, and survival. We will examine living armored creatures from around the world, understand how their armor works, and consider why, even in a world of rapid technological change and human dominance, armor remains a viable evolutionary strategy. The Cenozoic era, Mammals in ARMOUR, the Cenozoic era, which began 66 million years ago and continues to the present day, has been called the Age of Mammals. Following the extinction of the non-avian dinosaurs, mammals diversified to fill the ecological niches left vacant. This diversification led to the evolution of creatures of extraordinary size and diversity, and many of these creatures, particularly the larger herbivores and some predators, developed armor as a key component of their survival strategy. Beyond the glyptodonts that we discussed in Part 1, many other armored mammals evolved during the Cenozoic. In Asia, the Ankylosaurians, relatives of the glyptodonts, developed various types of armor. In Africa and Eurasia, various rhinoceroses evolved, and while not as heavily armored as glyptodonts or ankylosaurs, many rhinoceroses had thickened skin, and some developed horns or bony structures that served defensive purposes. One of the most remarkable developments during the Cenozoic of the Titanothers, massive, rhinoceros-like creatures that dominated many North American and Eurasian ecosystems during the early Cenozoic. These creatures reached enormous sizes, with some individuals weighing up to 20 tons. Many Titanothers developed thickened skulls and reinforced skeletal structures that provided protection. Some developed horns or bony protrusions on their heads. While not as visibly armored as glyptodonts, Titanothers nonetheless invested significantly in structural protection. The entelodonts, sometimes called hell pigs, were large omnivorous mammals that evolved during the Cenozoic in North America, Europe, and Asia. These creatures, some reaching lengths of up to 11 feet, had massive skulls with reinforced bone and numerous sharp teeth. While they were not heavily armored like glyptodonts, their robust skeletal structures constituted a form of protection. Their thick bones could withstand significant damage, and their massive heads could deliver devastating bites. In South America, the Macrauchenia were large camelid-like creatures that evolved during the Cenozoic. Some species of Macrauchenia developed thickened bones and robust skeletal structures that provided protection. These creatures occupied a similar ecological role to the Titanothers of North America and Eurasia, serving as large herbivores that were protected from predation partly through their size and partly through structural reinforcement of their skeletons. The Calicotheres were clawed, horse-like creatures that evolved during the Cenozoic. While not heavily armored, some Calicotheres developed reinforced forearms and claws that served both locomotor and defensive functions. These creatures could deliver powerful strikes with their claws, making them dangerous opponents for would-be predators. All of these creatures represent different approaches to protection in the Cenozoic. Some, like the glyptodonts, invested heavily in armor plates. Others, like the Titanothers and entelodonts, invested in robust skeletal structures and reinforced bones. Still others developed specific weapons like horns or claws that served defensive functions. What all of these approaches shared was a recognition that protection was important for survival, even in an era when the giant predators that had dominated terrestrial ecosystems during the Cretaceous had gone extinct. The evolution of modern armored FORMS, armadillos and their relatives, among all the armored mammals of the Cenozoic, none has persisted into the modern world more successfully than the Xenarthrans, the group that includes armadillos, anteaters, and sloths. The armadillos, in particular, represent a direct continuation of the armored mammal lineage, stretching back tens of millions of years to creatures like the glyptodonts. Modern armadillos are considerably smaller than their glyptodon ancestors, but they retain the fundamental armored design that made their ancestors so successful. The body of a modern armadillo is covered with bony osteoderms arranged in overlapping rows, covered by tough skin, creating a flexible armor that protects the creature while allowing movement. The head of an armadillo is also armored, with bony plates covering the skull. The tail of most armadillo species is also armored, consisting of rings of bone and tough skin. There are approximately 20 species of armadillos alive today, ranging in size from the tiny pink fairy armadillo, which weighs only about 3 pounds and measures roughly 4 inches in length, to the giant armadillo, which can weigh up to 140 pounds and measure nearly 5 feet in length. This diversity of sizes demonstrates that the armadillo body plan is flexible enough to support a range of different ecological roles. Different armadillo species have different armor configurations adapted to their particular lifestyles. The three-banded armadillo, native to South America, can curl into an almost impenetrable ball, presenting only its hardest armor plates to potential predators. This defensive behavior relies on armor that is appropriately configured to allow such curling. Other armadillo species have armor configurations better suited for burrowing or for moving through dense vegetation, with armor that is lighter and more flexible to allow for greater mobility. The armor of armadillos is not static. It is covered with tough skin that contains nerve endings, allowing armadillos to feel their environment. The armor can move somewhat, flexing to accommodate movement. This represents an elegant balance between protection and flexibility. The armadillo sacrifices nothing in terms of sensing its environment while maintaining substantial protection. The success of armadillos in the modern world demonstrates that armor remains a viable survival strategy. Armadillos occupy ecological niches, particularly as burrowing insectivores, that their armor helps them exploit effectively. The burrowing lifestyle requires a creature with strong limbs and a robust build, characteristics that armadillos possess. Their armor provides protection not only against predators but also against the rough, abrasive environment of their burrows and against the insects that they hunt, some of which can bite or sting. Armadillos have also proven remarkably adaptable to human-dominated landscapes. As humans have cleared forests and developed agricultural land in South and Central America, some armadillo species have not only survived but thrived. They continue to forage for insects and other invertebrates, their armor protecting them from both natural predators and the hazards of the human-modified environment. Pangolins, living fossils of mammalian armor. If armadillos represent one lineage of modern armored mammals, pangolins represent another, an equally remarkable but less well-known example of how armor continues to serve as a survival strategy in the modern world. Pangolins are the only living mammals that have developed scales as their primary defense mechanism. These scales, which are composed of keratin, the same material that makes up human fingernails and hair, cover the bodies of pangolins in a pattern of overlapping plates. There are approximately 8 species of pangolins alive today, distributed across Asia and Africa. They range in size from the long-tailed pangolin of Africa, which weighs only about 2 pounds, to the giant pangolin, which can weigh up to 85 pounds. Like armadillos, pangolins have evolved different armor configurations adapted to different lifestyles and ecological roles. The scales of pangolins are not like the scales of fish or reptiles. They are thicker, more rigid, and more densely packed. A pangolin is almost completely covered in scales, with the only significant unarmored areas being the underside of the body and the face. The scales are arranged in overlapping rows, much like roof tiles, creating a structure that sheds water and is extremely difficult to penetrate. The defensive effectiveness of pangolin armor is remarkable. A pangolin can curl into an almost impenetrable ball, with all of its vulnerable areas protected by scales. Even large predators have difficulty attacking a curled-up pangolin. The scales are so hard and so densely overlapped that few predators can find a weak point to exploit. Lions, tigers, and other large African and Asian predators generally give up on trying to prey on pangolins, recognizing that the energetic cost of attempting to breach the pangolin's armor exceeds the nutritional benefit of consuming the pangolin. Pangolins have another remarkable defense mechanism. They possess strong claws on their forelimbs that they use to dig into termite and ant mounds in search of food. These same claws can be used defensively, lashing out at predators with considerable force. Combined with their protective armor, these claws make pangolins formidable opponents. The success of pangolins demonstrates that novel armor designs can evolve even in comparatively recent evolutionary time. The scales of pangolins are thought to have evolved from modified hair, a unique solution that differs fundamentally from the osteoderms of armadillos or the exoskeletons of ancient arthropods. This innovation shows that evolution continues to discover new solutions to the problem of protection. Unfortunately, pangolins face significant threats from human hunting and habitat loss. They are among the most trafficked mammals in the world, hunted for their scales, which are used in traditional medicine, and for their meat. Many pangolin species are now endangered, representing a loss not only of remarkable creatures, but also of millions of years of evolutionary innovation. The persistence of pangolins into the modern world, despite these pressures, speaks to the fundamental soundness of their defensive strategy and their adaptability to changing conditions. Crocodilians, ancient armor persisting into the modern world. Among modern armored creatures, few have a lineage as ancient as the crocodilians. Crocodiles and alligators, along with their relatives like caimans and gharials, are living descendants of a lineage that extends back more than 200 million years. During the age of dinosaurs, their ancestors lived alongside dinosaurs, and they survived the KPG extinction that wiped out the non-avian dinosaurs. Crocodilians have persisted largely unchanged in their basic form for tens of millions of years, making them among the most successful and durable creatures in Earth's history. The armor of crocodilians consists of osteoderms, bony plates embedded in the thick skin of their bodies. These plates are arranged in rows running along the dorsal surface of the body, from the head to the tail. The osteoderms are not simply embedded in the skin, they are sutured together into the underlying bone, creating an integrated structure that is part of the skeleton itself. This integration creates an armor that is rigid enough to provide substantial protection, yet flexible enough to allow movement. The head of a crocodilian is also heavily armored, with the skull reinforced by numerous bones and the jaw muscles anchored to bony ridges that run along the sides of the head. This reinforcement allows crocodilians to generate enormous bite forces, among the greatest of any living animal. A large crocodile can bite with a force of thousands of pounds per square inch, enough to crush the bones of large prey. The tail of a crocodilian is also armored and muscular, serving as a powerful weapon for swimming and for attacking prey. The tail can deliver devastating blows, and the armor protects the tail itself from damage when it is used in this manner. Crocodilians are semi-aquatic creatures, spending much of their time in water but also coming onto land to bask, to breed, and to hunt. Their armor is well suited to this lifestyle. The smooth, streamlined form of the armor reduces drag in water, allowing for efficient swimming. The armor also protects against the rough, abrasive environment of terrestrial habitats, rocks, sand, and other surfaces that might damage more delicate skin. The success of crocodilians in modern ecosystems demonstrates that ancient armor designs can continue to be effective even after hundreds of millions of years. Crocodilians occupy the same ecological role today that they occupied millions of years ago. They are large aquatic predators that hunt fish, amphibians, reptiles, and mammals. Their armor remains as effective today as it was in the Mesozoic era. Modern crocodilians range in size from the dwarf caiman of South America, which reaches lengths of only about 5 feet, to the saltwater crocodile of Australia and Southeast Asia, which can exceed 20 feet in length. This size diversity, like the diversity of armadillos, demonstrates that the basic crocodilian body plan is flexible enough to support a range of different ecological strategies and environments. Crocodilians have also proven adaptable to changing human landscapes. While many have been hunted extensively, leading to population declines in some species, others have shown remarkable resilience. Some crocodilians have even thrived in human-modified environments, such as canals and reservoirs, adapting their behavior to exploit new resources created by human development. Turtles and tortoises, the perfection of shell armor. Turtles and tortoises, which we briefly discussed in Part 1, deserve further consideration because they represent perhaps the most successful armor design in the history of life. Turtles have persisted for over 200 million years, surviving multiple extinction events, and they continue to be abundant and diverse in the modern world. There are approximately 350 species of turtles alive today, inhabiting marine, freshwater, and terrestrial environments across the world. The shell of a turtle is unique among all armor designs. Unlike the external plates of other armored creatures, which can be shed and regrown, the turtle shell is an integral part of the skeleton. The upper part of the shell, the carapace, is formed from the fusion of the ribs and vertebrae. The lower part, the plastron, is formed from bones that develop in the skin. Both parts are covered with horny scutes made of keratin, similar to the scales of reptiles. This integration of the shell with the skeleton has profound implications for turtle biology. A turtle cannot leave its shell or replace it with a new one. Instead, the shell grows as the turtle grows, with the bones underneath expanding and the scutes developing new growth rings, much like tree rings. This continuous growth without shedding eliminates the vulnerability of molting that plagues other armored creatures. The effectiveness of the turtle shell is demonstrated by its persistence and success. Turtles have survived in relatively unchanged form for millions of years. The Galapagos giant tortoises, among the longest-lived vertebrates, can live for over 100 years. Their large size and slow reproduction make them vulnerable to extinction, yet they have persisted despite intense hunting by humans. The mere fact that they continue to exist demonstrates the effectiveness of their armor in protecting them from predation. Different turtle species have different shell designs adapted to their particular ecological roles. Marine turtles like the green turtle and the loggerhead turtle have relatively streamlined shells that reduce drag in water. Their shells are somewhat flattened and do not close completely, as the creatures are rarely able to fully retract into their shells. Instead, they rely on their aquatic lifestyle and their ability to swim away from predators to escape danger. Freshwater turtles like the painted turtle and the red-eared slider have more domed shells that provide better protection. Many can partially or fully retract into their shells. Their shells often have patterns and colors that provide camouflage in their freshwater habitats. Terrestrial tortoises like the giant tortoises and the leopard tortoise have extremely domed, heavy shells that provide maximum protection. These creatures are slow-moving and cannot escape predators through speed. Instead, they rely entirely on their shells for protection, withdrawing into them when threatened. The shell becomes a miniature fortress that can protect the animal from large predators. The diversity of turtle shell designs demonstrates that the basic turtle body plan is flexible enough to be adapted to different environments and ecological roles. Yet the fundamental design, the integration of the shell with the skeleton, has remained constant for millions of years. This constancy suggests that the design is not just effective but optimal for what turtles do. In the modern world, turtles face significant threats from human activity. Habitat loss, pollution, hunting, and climate change have led to population declines in many species. Several species of sea turtles are endangered or critically endangered. Freshwater turtles are also facing pressures, yet many turtle species continue to persist and even to thrive in human-modified landscapes. Painted turtles, red-eared sliders, and other common species are abundant in ponds, lakes, and rivers across much of the northern hemisphere. Their persistence demonstrates that armor, combined with appropriate behavior and physiology, can allow creatures to survive in a world increasingly shaped by human activity. Modern fish armor, continuation of ancient designs. While much of our discussion has focused on land animals, we must not forget that the oceans continue to be home to armored creatures. Many modern fish maintain armor designs that have persisted for millions of years, demonstrating that marine environments continue to select for protective structures. Catfish, for example, have developed bony plates called ganoid scales that provide protection. These scales, which are thicker and harder than the scales of most fish, are inherited from ancient armored fish. Some catfish species are heavily armored, with their bodies nearly encased in protective plates. Others are more lightly armored. The diversity of catfish suggests that the level of armor investment varies depending on the ecological niche and predation pressure that each species faces. Pufferfish have evolved a remarkable defense mechanism. They can inflate their bodies when threatened, increasing their apparent size and making it difficult for predators to swallow them. Some pufferfish species also have spines that become exposed when they inflate. While not armor in the traditional sense, this defense mechanism serves a similar purpose. It makes the pufferfish a difficult target for predation. Some modern fish have evolved bony plates that serve protective functions. The seahorse, for example, has a body covered with bony plates that give it a distinctive shape. These plates provide protection and also serve to camouflage the seahorse by creating a bumpy outline that blends in with seagrass and coral. Armored catfish of the genus Loricaria, found in South American rivers, have bodies almost entirely covered with bony plates arranged in overlapping rows. These fish feed on the bottom of rivers and streams, where they are exposed to predation from larger fish and from terrestrial predators like caimans. Their armor provides protection in this dangerous environment. The persistence of armor in modern fish demonstrates that predation pressure remains significant in marine and freshwater environments. While many modern fish are fast-moving and rely on speed to escape predators, others have chosen the opposite strategy, remaining slow but heavily protected. This diversity of strategies shows that multiple solutions to the problem of survival continue to be effective. Invertebrate armor in the modern world. Much of our discussion has focused on vertebrates, fish, reptiles, mammals, and other creatures with backbones. However, we must not neglect the enormous diversity of armored invertebrates that continue to thrive in the modern world. Arthropods, insects, arachnids, and crustaceans represent the most diverse group of animals on Earth, with over 1 million described species. Many of these have exoskeletons made of chitin, the same material that made the exoskeletons of trilobites so effective hundreds of millions of years ago. Modern arthropods demonstrate that the exoskeleton design is not merely ancient history, but a continuing evolutionary success. Beetles, the most diverse group of animals on Earth with over 400,000 described species, have exoskeletons that are often thickened and reinforced to provide protection. Some beetles have developed elaborate spines, ridges, and other structures that make them difficult to attack. The armor of beetles is particularly sophisticated, with different parts of the body having different thicknesses and textures optimized for different functions. The head and thorax are often heavily reinforced, protecting vital organs and the musculature that powers movement. The elytra, the hard forewings that protect the delicate flying wings, are often reinforced for protection while remaining light enough to allow flight. Crustaceans like crabs and lobsters have exoskeletons made of chitin reinforced with calcium salts, making them extremely hard and durable. These creatures often develop additional armor in the form of spines and ridges. Some crabs have exoskeletons so heavily reinforced that they are nearly as hard as rock, providing protection against predators with powerful claws or crushing jaws. Mollusks, including clams, mussels, and snails, have developed shells made of calcium carbonate that provide exceptional protection. Some mollusks, like the conch, have shells so thick and strong that they are nearly impossible for predators to penetrate. Mollusks have carried forward the ancient design principle of the shell, which evolved with creatures like trilobites and refined it over hundreds of millions of years. Echinoderms like sea urchins have developed spines and bony plates that provide protection. Some sea urchins have extremely long, thin spines that make it difficult for predators to get a grip on the soft body hidden beneath. Others have shorter, more robust spines. The diversity of spine designs demonstrates that evolution continues to refine and adapt this ancient defensive mechanism. The persistence of these invertebrate armor designs demonstrates that armor at all scales, from the exoskeletons of insects to the shells of mollusks to the plates of crustaceans, remains effective in the modern world. These creatures do not represent evolutionary relics from a distant past, but rather active, successful, and diverse parts of modern ecosystems. The porcupine and other mammalian quills. While discussing modern armor, we should mention one more remarkable mammalian defensive structure. Quills. Porcupines, which are found in both North America and Africa, have evolved modified hairs called quills that serve as defensive weapons. These quills are essentially thickened, hollow hairs with barbed tips. When a porcupine is threatened, it raises its quills, making itself appear larger and more formidable. If a predator attacks, the quills become embedded in the attacker's skin, causing irritation and pain. Porcupine quills represent a different approach to armor than the plates of glyptodonts or the scales of pangolins. Rather than attempting to create an impenetrable fortress of rigid structures, porcupines have evolved a defense that is lightweight, flexible, and highly effective. A porcupine can move through dense vegetation easily, and the quills do not impose the metabolic cost of maintaining heavy bone or keratin plates. The effectiveness of porcupine quills is demonstrated by the rarity of predators that regularly hunt porcupines. Most large predators avoid them. Even large cats and canids recognize the danger and usually leave porcupines alone. Among the few predators that regularly hunt porcupines are the fisher cat, a mustelid that is relatively immune to quill injuries, and occasionally large birds of prey that can attack from above, where the quill defense is less effective. Quills also appear in hedgehogs and echidnas, other mammalian lineages that have independently evolved this defensive strategy. This repeated evolution of similar defensive structures in different lineages demonstrates that quills represent a sound solution to the problem of protection, so sound that multiple lineages have discovered it independently. Structural armor, bones and muscle. Not all modern armor takes the form of external plates, scales, or shells. Many modern creatures rely on structural armor, thickened bones, reinforced muscles, and powerful builds that serve defensive purposes. Rhinoceroses, for example, have extremely thick bones and powerful musculature that protect them from damage. Their hide is thickened and tough, providing some protection against predators and against the rough environments they inhabit. Hippopotamuses have extremely thick skin, sometimes reaching lengths of nearly 2 inches, that is both protective and contains oil glands that help prevent cracking and infection. Their massive, powerful jaws serve both predatory and defensive functions. A hippopotamus can deliver devastating bites that few African predators can withstand. Gorillas and other great apes have developed powerful musculature and robust skeletal structures that serve defensive purposes. While not as visibly armored as many of the creatures we have discussed, these large primates are formidable opponents for would-be predators, capable of delivering powerful blows with their arms and bodies. These examples demonstrate that armor is not limited to external structures like plates and shells. Internal skeletal and muscular modifications can also serve protective functions, and many modern creatures rely on such structural armor to supplement or replace external armor. Why armor persists: the balance of costs and benefits. Having surveyed the diversity of armored creatures in the modern world, from armadillos to pangolins to crocodilians to insects and beyond, we should consider the fundamental question: why does armor persist as a survival strategy in the modern world? Why do creatures continue to invest resources in protective structures when they could use those resources for other purposes like reproduction, sensory development, or enhanced mobility? The answer lies in understanding that armor provides benefits that, in appropriate ecological contexts, outweigh the costs. Let us consider some of these benefits and costs in more detail. The primary benefit of armor is, of course, protection from predation. A heavily armored creature is less likely to be successfully hunted than an unarmored creature of similar size. Predators often look for vulnerable prey, and an armored creature, by definition, is less vulnerable. This means that armored creatures can often survive at higher population densities than unarmored creatures because more individuals can survive predation. A secondary benefit of armor is protection against environmental damage. Armor protects against abrasion, which is particularly important for creatures that live in rough environments like rocky shorelines or arid deserts. Armor also protects against sunburn and desiccation, which is important for creatures that spend extended periods exposed to sunlight. Armor can also serve structural purposes, particularly in large creatures. The reinforced skeleton of a large creature like an elephant or a hippopotamus provides support for the enormous weight of the body. Armor can also provide anchoring points for muscles, allowing those muscles to generate more force. However, armor also imposes significant costs. The primary cost is metabolic. Producing and maintaining armor requires energy. This means that an armored creature must consume more food than an unarmored creature of similar size. In environments where food is scarce, this cost can be prohibitive. A secondary cost of armor is reduced mobility. An armored creature is heavier and often less flexible than an unarmored creature. This means that armored creatures are generally slower and less agile. For creatures that rely on speed to capture prey or to escape predators, this cost can be fatal. Armor also imposes constraints on body shape and structure. An exoskeleton must be shed and regrown as the creature grows, creating vulnerable periods. An internal skeleton integrated with armor, like the skeleton of a turtle, constrains how the creature can move and what body shapes are possible. The balance between these costs and benefits determines whether armor is a good strategy for a particular species in a particular environment. For large creatures in resource-rich environments with significant predation pressure, armor is advantageous. For small creatures in resource-poor environments, or for creatures that rely on speed for hunting or escaping predators, armor may be disadvantageous. The diversity of strategies we see in the modern world, armored creatures coexisting with fast, unarmored creatures, demonstrates that multiple solutions to the problem of survival can be effective simultaneously. Evolution is not searching for a single optimal solution, but rather exploring the space of possible solutions, with different solutions being optimal in different contexts. The modern threats to armored creatures. As we consider the persistence of armor in the modern world, we must also consider the threats that armored creatures face in the contemporary era. The world has changed dramatically over the past few thousand years, with the emergence of human civilization, and particularly in the last few centuries with industrialization and globalization. Many armored creatures face habitat loss as their environments are converted to human uses. Forests are cleared for agriculture. Wetlands are drained for development. Rivers are dammed for hydroelectric power or water supplies. The result is that creatures that evolved in particular habitats can no longer find suitable places to live. Pollution poses another threat. Persistent organic pollutants accumulate in the tissues of armored creatures, particularly aquatic species like turtles and crocodilians. These pollutants can cause developmental problems, reproductive failure, and immune system suppression. Plastics in the ocean are ingested by sea turtles, causing intestinal blockages and death. Chemical pollution in rivers affects freshwater turtles and crocodilians. Climate change poses a particularly profound threat. Many armored creatures have specific temperature requirements. Some reptilians determine the sex of their offspring based on the temperature at which eggs are incubated. As global temperatures rise, the sex ratios of populations can become skewed, with potential consequences for long-term population viability. Changes in rainfall patterns affect the availability of water for aquatic species. Changes in seasonal timing can disrupt the breeding cycles of many creatures. Hunting and overexploitation pose direct threats to many armored creatures. Turtles are hunted for their meat and eggs in many parts of the world. Crocodilians were hunted extensively in the 20th century for their skin, which was made into leather goods. Many pangolin species are hunted for their scales and meat. While hunting has decreased in some regions due to conservation efforts, it continues in others, and in some cases, hunting pressure is actually increasing. Invasive species pose an indirect threat. Non-native predators introduced to islands or isolated habitats can devastate populations of armored creatures that evolved without natural predators. For example, introduced rats prey on turtle eggs and hatchlings, dramatically reducing recruitment in some populations. Disease can also affect armored creatures. Ranavirus, a virus that affects reptiles, has caused mass die-offs in some turtle populations. Parasites and other pathogens can reduce the fitness of armored creatures, making them more vulnerable to predation and other causes of mortality. The cumulative effect of these threats is that many armored creatures are now endangered or critically endangered. Several sea turtle species are at risk of extinction. Some crocodilian populations have been severely depleted, though some have recovered due to conservation efforts. Pangolins are among the most threatened mammals, with populations declining in many regions. Even some armadillo species are declining due to habitat loss and hunting. Conservation and the future of armored creatures. In response to these threats, conservation efforts have been undertaken to protect armored creatures. International trade in endangered species is regulated by the Convention on International Trade in Endangered Species of Wild Fauna and Flora, commonly known as CITES. Many armored creatures are listed on CITES, restricting or prohibiting their trade. Protected areas have been established to preserve habitats for armored creatures. National parks and wildlife reserves provide safe havens for species that might otherwise be hunted to extinction. These protected areas are crucial for the long-term survival of many species. Breeding programs have been established for some endangered armored creatures. Zoos and research institutions breed endangered sea turtles, crocodilians, and other species, with the goal of eventually reintroducing animals into the wild. These programs have had varying levels of success, but they represent important efforts to prevent extinction. Community-based conservation programs have also been effective in some regions. By involving local communities in conservation efforts and by providing economic incentives for protecting armored creatures, conservation organizations have achieved success in reversing population declines in some species. Scientific research continues to improve our understanding of the biology, ecology, and threats facing armored creatures. This research informs conservation strategies and helps identify the most effective approaches to protecting endangered species. Despite these conservation efforts, the future of many armored creatures remains uncertain. Habitat loss continues at a rapid pace. Climate change continues to accelerate. Human populations continue to grow, increasing pressure on natural ecosystems. Whether armored creatures will continue to thrive in the modern world depends on whether humans will commit to protecting them and preserving the habitats they depend on. Lessons from armored creatures. What evolution teaches. As we conclude our examination of the forgotten age when creatures wore armor, and as we reflect on the persistence of armor in the modern world, we should consider what armored creatures teach us about evolution, adaptation, and survival. First, armored creatures demonstrate that there are multiple valid strategies for survival. Armor is not the only solution to the problem of protection. Speed, intelligence, camouflage, toxins, and a multitude of other adaptations also serve defensive functions. The success of both armored and unarmored creatures in modern ecosystems demonstrates that evolution is not searching for a single optimal solution, but rather exploring the space of possible solutions, with different solutions being optimal in different contexts and at different times. Second, armored creatures demonstrate that evolution can discover similar solutions independently. The shells of turtles and mollusks, while built on different skeletal foundations, serve similar defensive functions. The scales of pangolins and the osteoderms of armadillos represent different ways of achieving similar protection. The spines of sea urchins and the quills of porcupines represent different solutions to similar problems. This convergent evolution suggests that some solutions are particularly effective and that evolution tends to converge on these effective solutions when facing similar challenges. Third, armored creatures demonstrate that success is not permanent. The placoderms dominated the oceans for hundreds of millions of years, yet they went extinct when environmental conditions changed. The dinosaurs, including the heavily armored Ankylosaurs and ceratopsians, dominated for over 160 million years, yet they too went extinct. The glyptodonts persisted for tens of millions of years, yet they are now extinct. Even the most successful designs, adapted to particular conditions, are vulnerable to changing conditions. Fourth, armored creatures demonstrate that every adaptation represents a trade-off. Armor provides protection, but at the cost of reduced mobility, increased metabolic demands, and constraints on body shape. Creatures must balance the benefits of protection against these costs, with the optimal balance depending on the particular ecological circumstances they face. Fifth, armored creatures demonstrate that evolution is conservative. Once a successful design is discovered, it tends to persist with relatively minor modifications. Turtles have remained fundamentally unchanged for hundreds of millions of years. Crocodilians have persisted largely unchanged for tens of millions of years. This conservatism reflects the fact that once a design is well adapted to its ecological role, major modifications are less likely to be advantageous than minor tweaks. Sixth, armored creatures demonstrate that evolution is not progressive, that later creatures are not necessarily better than earlier creatures. Trilobites were not inferior to modern arthropods. Placoderms were not inferior to modern fish. Indeed, many modern creatures are very similar to their ancient ancestors. The persistence of similar designs over millions of years suggests that these designs are effective solutions, not primitive precursors to more advanced forms. Finally, armored creatures demonstrate that the history of life is not a linear progression from simple to complex or from primitive to advanced. Instead, it is a history of exploration, of evolution discovering different solutions to the problem of survival, refining these solutions, and when conditions change, sometimes discovering entirely new solutions. Some of the most primitive solutions, like the exoskeleton or the shell, have proved so effective that they have persisted for hundreds of millions of years and continue to be used by modern creatures. The changing world and the persistence of armor. As we contemplate the future of armored creatures in a world increasingly shaped by human activity, we might wonder whether armor will continue to be a viable strategy. Some would argue that in the modern world, with its rapid environmental changes and human pressures, the specialized adaptations of armored creatures may be liabilities rather than assets. Armor, they might suggest, is an ancient strategy that belongs to a bygone era. However, the evidence suggests otherwise. Armored creatures continue to thrive in the modern world, even in human-dominated landscapes. Armadillos have expanded their range northward, likely in response to climate change. Some crocodilian populations have recovered from near extinction and are now expanding their ranges. Turtle populations, while declining in some regions, remain abundant in others. The simple fact that armored creatures continue to persist and even to thrive in the modern world suggests that armor remains a viable strategy. Moreover, human activity, while generally negative for wildlife, has inadvertently created new opportunities for some armored creatures. Reservoirs and artificial wetlands created for human water management have become important habitats for turtles and crocodilians. Agricultural ponds often support thriving populations of armadillos and other creatures. Humans have also established protected areas and sanctuaries that provide refugia for endangered armored creatures. The persistence of armor in the modern world suggests that the adaptive principles that have driven the evolution of armor over millions of years continue to operate. Where there is predation pressure, armor remains an effective defense. Where there are resources to support the metabolic costs of armor, armor can be maintained. Where environmental conditions are stable enough to support specialized adaptations, armor provides advantages. Concluding reflections, the forgotten age and the eternal present, the age when creatures wore armor is not forgotten. It persists in every turtle that basking on a log, in every crocodile lurking in a river, in every armadillo burrowing through soil, in every pangolin curled into a protective ball. These modern creatures are not relics of a distant past, but rather living witnesses to a strategy that has proven so effective that it has persisted virtually unchanged years. The history of armor is a history of survival, of adaptation, and of the infinite creativity of evolution. From the simple shells of Cambrian creatures to the sophisticated plates of Devonian placoderms, from the complex armor of dinosaurs to the elegant shells of modern turtles, armor has proven to be a strategy effective enough to persist through changing environments and changing predators. Yet armor is also a history of limits. The most heavily armored creatures are not necessarily the most successful. The most specialized designs are vulnerable to environmental change. The creatures that have persisted longest are often those that found a balanced approach, investing in protection without sacrificing all mobility or flexibility. In a world increasingly shaped by human activity, armored creatures face unprecedented challenges. Habitat loss, pollution, climate change, and hunting threaten the survival of many species. Whether these creatures will persist into the distant future depends on decisions that we make today about conservation and protection. But regardless of what the future holds, the history of armor tells us something profound about life on Earth. It tells us that creatures are not passive recipients of their environment but active participants in their own survival. It tells us that natural selection has discovered multiple valid strategies for existence, and that diversity, not uniformity, is the hallmark of evolutionary success. The armored creatures of the modern world are the inheritors of a legacy stretching back over 500 million years. They are the living embodiment of one of evolution's most enduring and successful strategies. To understand them is to understand something fundamental about the nature of life itself. Epilogue, the eternal cycle. As we bring this documentary to a close, we return to where we began, with the question of why creatures wear armor. The answer, we have seen, is complex and multifaceted. Armor serves to protect creatures from predation, from environmental damage, and from the rigors of their particular habitats. Armor allows creatures to exploit ecological niches that would be impossible without protection. Armor represents an investment in survival that, for millions of creatures and across hundreds of millions of years, has proved worthwhile. But armor also tells us something about the nature of life itself. Life on Earth is fundamentally competitive. Every organism is in competition with every other organism for resources, for space, for reproductive success. In this competitive struggle, evolution has discovered countless strategies. Some creatures rely on speed, some on intelligence, some on toxins, some on size, and some, the armored creatures, rely on protection. The persistence of armor through geological time, through extinction events, through the rise and fall of dominant life forms, suggests that armor addresses a fundamental challenge that any creature must face: the need to survive in a world full of other creatures that are trying to consume it or displace it. This challenge has not changed in hundreds of millions of years, and there is no reason to believe it will change in the future. The creatures we see today, wrapped in their shells, plates, and scales, are the products of millions of years of evolution. They represent countless small refinements, countless successful innovations, countless elegant solutions to the problem of protection. To see an armadillo burrowing through soil, a turtle basking on a log, a crocodile floating in a river, is to see a window into deep time, to see creatures that are in many ways very similar to their ancestors of tens of millions of years ago. Yet these creatures are also very much modern animals, adapted to the conditions of the world they inhabit today. They face challenges their ancestors never faced. They live in a world transformed by human activity. They navigate landscapes fragmented by human development, and yet they persist, they adapt, they continue to survive as they have survived for so long. This persistence is a testament to the fundamental soundness of their design, but it is also a challenge and an opportunity for those of us who share the world with these remarkable creatures. If we value the persistence of life in all its diversity, if we recognize the elegance and effectiveness of the strategies that evolution has discovered, then we have a responsibility to protect the creatures that embody these strategies. The age when creatures wore armor may be a forgotten age, but the creatures themselves are alive and present in the world today. And in protecting them, we protect not just the individual species but the evolutionary innovations that they represent, innovations that have taken millions of years to perfect and that cannot be recreated if once lost. The forgotten age is not truly forgotten. It lives on in every armored creature that survives in the modern world. And as long as these creatures persist, the history of armor, a history spanning over 500 million years, continues to be written, chapter by chapter, generation by generation, in the bodies and behaviors of the creatures that wear it. Thank you for joining us on this journey through deep time and across the vast diversity of life. We hope this documentary has given you a new appreciation for the forgotten age when creatures wore armor, and for the armored creatures that continue to persist in our modern world. Please share this video with others who might be interested in the history of life and evolution. And if you have encountered any armored creatures in your own life, a turtle, an armadillo, a crocodile, a beetle, an insect of any kind, take a moment to appreciate the remarkable evolutionary heritage that they carry, the solutions to survival that their bodies embody, and the millions of years of history that they represent. Until next time, thank you for watching, and we look forward to exploring more of the remarkable stories of life's history with you. Welcome to a journey through deep time, where the very concept of survival meant wrapping yourself in nature's most sophisticated engineering. This is The Forgotten Age When Creatures Wore Armor, a documentary that explores one of evolution's most profound and persistent strategies, the development of protective biological structures that have shaped life on Earth for nearly 600 million years. For most of human history, we've marveled at the bones of ancient creatures, often focusing on the size of their teeth or the power of their limbs. But there's another story, one equally dramatic, equally important, and far more enduring. It's the story of armor. Not the armor forged by human hands in castles and battlefields, but armor grown from living tissue, sculpted by natural selection, and refined through countless generations until it became a masterpiece of biological engineering. Some of these armored creatures dominated their worlds for hundreds of millions of years, far longer than any other dominant life form we know of. And though many have faded into extinction, their legacy persists in the living armored animals that walk, swim, and crawl across our world today. This documentary will take us from the moment the first predators emerged in Earth's oceans, spurring an evolutionary arms race that would revolutionize life itself. We'll examine how simple shells became sophisticated exoskeletons. We'll watch as fish developed heavy plating, as reptiles grew thick hides and bony protrusions, and as mammals created some of the most unusual defensive structures ever to evolve. We'll see how environmental pressures shaped these remarkable adaptations, and why, despite their apparent invulnerability, so many of these armored giants ultimately succumbed to extinction. And we'll discover why even today, after all these millions of years, creatures continue to invest in armor as a survival strategy. Please let us know in the comments where you are watching this history video and what time you are watching it, and be sure to subscribe to the channel for future videos. Now, let's begin our exploration of the age of armor. Part 1: The Genesis of Defense. To understand why armor became so important in the history of life, we must first understand the world before it. For the first 3 billion years of life's existence on Earth, creatures were soft-bodied. They were simple. Bacteria, algae, sponges, and other early organisms floated and crawled through the oceans without any rigid structures. There were no teeth, no claws, no hard parts at all. And in this world, there was little need for defense because there were few predators capable of hunting anything larger than themselves. But something profound changed around 540 million years ago, during a period